So this is what we discuss now, Feynman's suggestion. Feynman's suggestion says that this Dirac's answer is true. First of all, this answer is true when TF is infinitesimally close to TI. This is the result for that. So you have XF TF is equal to TI plus epsilon, where epsilon is infinitesimal. Xi TI is equal to a some constant e to the power I by h bar s x lower bar, where x lower bar is the classical path connecting two infinitesimally close points. So this is the classical path connecting xi ti and xf ti plus epsilon, these two infinitesimally close points, and so this epsilon is infinitesimal. So so to draw a picture like earlier, so what you are doing here is there is a path here, but then there is this. So this is xi and this is xf. This is ti and this is tf, which is ti plus epsilon. And between these 2 points, so the path that you are considering in order to calculate the phase is x lower bar as a classical trajectory, okay, between these 2 points. Now, what about the finitely separated events then? So for finitely separated events, let us try to see what result one should get. So earlier we drew this picture here. This is called time slicing. So I'm the entire time interval ti to tf, I'm slicing it in, say, n capital N steps. Okay. So if you are asking this question here, what would be this matrix element? There is no fixed value of n, because n is your slicing. This does not depend on n, right? So ideally speaking, just like the concept of integration, you should slice n in n times, then do certain operation calculations, and that will only give you an approximate result for the matrix element, and you should be taking n going to infinity limit. And we saw exactly that here. Here we are, you see, if this is an exact statement, here there are n steps, n slices. So this is an exact statement. There is no problem with that. I am not taking any n going to infinite limit here. However, if you would like to use Dirac's proposal modified by Feynman and write these matrix elements in terms of this phase where action is sitting, then these 2 points must be infinitesimally close to each other, and that you cannot maintain with a finite n if the time difference Tf minus Ti is finite. If this is finite, you have to allow large number of points, n must be going to infinity, and then each matrix element becomes corresponding segment becomes infinitesimal, and then you can use this expression to do to calculate that to calculate that matrix element. Okay, so therefore what I'm doing now, limit n going to infinity, but n times epsilon going to Tf minus Ti, which is of course finite, then a to okay, then integral product over j equals 1 to n minus 1 dxj, and then there's infinitesimal matrix elements, okay, or matrix elements corresponding to infinitesimal segment is given by t, the integral dt ti to tf l x dot t, and so I'm writing that matrix element in using this proposal of Feynman, and therefore there will be a to the power n in front. A is a constant. Okay. So this is an operational definition of this thing. Now you see there are integrations on these intermediate points. The intermediate points are integrated over. However, if you choose some values of these intermediate points, because this thing goes the whole range, so if you choose these values differently, like arbitrarily, okay, then that corresponds to a different path. Okay, so this is why, but all these paths will have the same initial and final points. Those are the boundary conditions. The entire result depends only on the boundary conditions. So these are the boundary conditions. Boundary conditions for the path. Allowed paths. For the allowed paths, but doing that integration among over the intermediate points, this x1, x2, etc., actually doing that integration is allowing you to consider other paths, because they are not fixed to any x1 tilde x2 tilde fixed values, but they are integrated over. Okay, now so that's why this whole set of the set of all these integrals together is actually integrating over path over a path connecting these 2 points. So this infinite number of, in the large n limit, there are infinite number of integrations. So those are infinite number of integrations actually is equivalent to a single integration on the curly f space, because there each path is a single point. So if you are doing an integration in the curly f space, in this space, you are doing an integration, ordinary integration in this space. Okay, because at each point different paths correspond to different points. Okay, so there's infinite number of integrals appearing here is actually a in a sense, in a suggestive manner, is a single integral on the space of curly f, and that is called a path integral. So we write it as curly d of x e to the power I by h bar s of x. Because you are doing the path integral, of course, although for each segment you are taking the classical path connecting the consecutive points, but the entire path is not a classical path. Okay, that taking the classical path between the consecutive points is just an approximation method now. But that since that segment width of the segment is going to go to 0 in this epsilon going to 0 limit, large n epsilon constant means epsilon goes to 0. In that limit, exactly which path you take should not matter, and it will give you the arbitrary paths all connecting these two boundary points. So the entire path is not classical. Only the segment, each segment you're taking a classical path connecting them, and that's just an approximation procedure. So this is called Feynman's path integral. And this can be interpreted as an integration over that curly f. It's an infinite dimensional space. It's an integration in an infinite dimensional space. We call it, okay, so you see there is a complicated procedure. It is not easy to define what exactly one means by this. It is the same mathematical complication of doing an integration in an infinite dimensional space. And the problem is to make sense of this entire thing. There are n minus 1 number of integrations, and then there is a factor a to the power n. All together you are calling it dx. Okay, so it includes, this is a measure, this includes everything here. Okay, so operationally the way you would do is that when the dynamical system is fixed by the action or this Lagrangian, then you take a finite value of capital N and do this calculation, and then you take another value which is larger than the previous value, do the calculation again. So you do the calculation for different values of capital N and keep increasing the value of capital N and see if the result is approaching a particular limit. It is that limiting result that is the right answer for this one. This is what it means. And of course, a is an arbitrary number. Question is that how to fix a, because this a actually defines what the measure is, partially at least. So to find a, you demand equality with the result coming from the usual Schrodinger theory. So in case where you can do the calculation using the usual Schrodinger theory, that means in a case where you can do the calculation in both the languages, in both the methods, and then the result should match. So a can be fixed by matching result obtained from usual Schrodinger theory. If you have any situation where you cannot use the usual Schrodinger theory, but there are certain parameters in your theory such that you can take particular limit in those parameters, and in that limit you can do the calculation for the from the usual Schrodinger theory. Then you can calculate A in that limit, um, and and because of the continuity, the same value of A should hold when you change the parameters to other values where you do not have a calculation for from the usual Schrodinger theory. That is one way of dealing with it, but nonetheless, this is a computationally, or in terms of definition, what the definition is a complex issue, and one has to deal with it. However, even if you can do a calculation within Schrodinger theory, this actually this picture of Feynman's path integral gives an alternative interpretation, conceptual picture of quantum mechanics, which is obscure in usual Schrodinger theory. Now you are saying that the particle is moving from here to here, and all sorts of paths are actually contributing to the amplitude. Only one of them is a classical path, but there are infinitely many other paths, and they are all coming from the form of the action. And they are all relevant, and each one of them is contributing in quantum mechanical amplitude. What else do I need to mention here? And so going back, okay, two things. Going back, earlier we said that in classical mechanics only the extremum or the minima of the action are important. The entire form of the action is not. That is not true, because that entire form of the action is what is responsible for this statement, that it generates canonical transformation from one time to another. And in quantum mechanics, the dependence on the detailed form of the action is more manifest, because all the non-trivial other paths which are characteristic of the form of the action, not only its extrema value, not only where the extrema lie, but about all the other paths. Action knows about all the other paths, and those paths are contributing to the amplitude. Okay, now let me explain the last thing, explain the stationary phase argument. So stationary phase argument can be understood from this expression very easily. You see, in the h bar going to zero limit, so you could think of, so this is a phase e to the power I theta, where theta is s divided by h bar. In the h bar going to zero limit, s over h bar is very large, so theta is very large. Now, what do you mean by theta very large? Theta is a variable because you are varying the path, therefore s is varying, and therefore theta is varying. Now, if theta is very typical, so when you change the path slightly, so then this s will change slightly, but h bar being very small, it becomes a large number. So the change, so even if you vary the path by a small amount, the phase or the angle theta is changing wildly. But this is a phase, which means its real part is cosine theta and imaginary part is sine theta. So each of these two values will be fluctuating between -1 and +1. So if theta changes wildly, then the entire range of -1 to +1 is being covered. And therefore, for small variation of the path, all possible values between -1 and +1 are randomly appearing. And since, because of the distribution is symmetric in the negative side and positive side, they will cancel, and the result will be 0. So in the h bar going to zero limit, you would expect there's a wildly fluctuating phases. Of course, there is a difficulty in doing the calculation mathematically, but you can have a mathematical argument, which we will do eventually later on, a more rigorous mathematical argument, which will incorporate this conceptual idea that I'm saying. You guide the mathematical argument of doing that calculation, wildly fluctuating integration of wildly fluctuating phases. You define more rigorously a process of doing that calculation in such a way that this feature is preserved. The expectation that that in the h bar going to 0 limit, when you vary the paths in a slightly, all possible phases will randomly appear and cancel each other between -1 and +1. This argument will fail only in the case when your x is a classical trajectory, because classical trajectory means the action is extremum. In a near an extremum, the variation of the action is slow. So therefore, even if you slowly change the path from the classical path, classical trajectory, the change in ace will be slow. And because of that, value at the classical trajectory will not be cancelled by any competing value. So the only contribution that will remain are the ones that come from the classical trajectories. So this is because the phase is stationary at the classical trajectory, and it does not wildly fluctuate. There is no cancellation, and therefore only the stationary phases remain in the result. And that is what we were discussing earlier. So that is the stationary phase argument. Okay.